I guess to introduce myself, my name is Kevin Winter. I'm a PhD student at University of Massachusetts Amherst, advised by Dr. Dan Sheldon. Before I get started, I just wanted to take a second to plug this series. So we've had a lot of really great talks in the Open Graduate Seminar series so far. But if any of you are grad students or no grad students who are interested in speaking at the seminar series from your lab or your department or other departments, we would be very happy to have you. I think we have some availability later in the summer or at the beginning of next semester. So if you're interested or you know someone who is, please get in touch with me or one of the other organizers, and we can work out a way for you to come present your work. Yeah, okay. So with that, let's get started. So today I'm going to talk about my longest running project. Dan and I have been working on this for the last 3 years. And broadly, we're interested in developing statistical tools for doing inference and learning using generating functions for models of population dynamics. So what do I mean by population dynamics? Can you guys see my mouse?
I can.
You can, okay. Thanks, Rita. Okay, so population dynamics look something like this. So we have a population of some animal that we are interested in studying. And we're looking at the population of that animal in some given habitat patch. And if we look at that data continuously, we see that it looks like a discrete valued step function that changes continuously over time. So at any given time, it can either increase by 1 or decrease by 1. The number of animals that are in the population at any given time is called the abundance, and it's the main statistic that we're interested in modeling. So that, sorry?
And why is it that it can increase only by 1?
We treat it like it can increase by 1. Here in our models, an animal can give birth to several at once. So this data is actually simulated, and some of our other simulations allow for what do you call them? Litters or something like that, where you have one animal gives birth to several. But for now, we're just treating it as this kind of step function.
Okay, thanks.
Yeah, it's a good question. So the main dynamics that we are interested in modeling that govern how this abundance changes over time are immigration, reproduction, and death/immigration. So immigration is obviously new animals from outside the habitat patch who are moving in. Reproduction is some of the animals in the population reproducing. In this case, we're going to assume that they reproduce asexually, just to simplify the math and the model. And then death and emigration are pretty indistinguishable for us. So we're going to kind of treat them as one process, animals leaving the population. And so with models like this, we're going to be interested in asking questions like, over time, over maybe several years that we've been observing this species, how is the population doing? Is it on the decline? Is it at risk of going extinct in this one patch? Is it at risk of exploding? Are we going to have more animals in this population than the habitat can support? And if these things are happening, maybe we want to ask questions like, well, what would happen if we were able to reduce emigration out of the habitat patch, or if we were able to curtail reproduction so that it was kept at a more manageable rate. So the data that we actually looked at, so this would, let's see. So if you had like a captive population where you were able to observe all the animals all the time with trained zookeepers or something, you might actually be able to get this kind of continuous data set. But in our case, that's pretty infeasible. So what we actually have typically in our case is we send out maybe once a week, we'll send out a survey team, and they will go and observe the population and record how many animals were there at any given, on the day that they went and observed the population. So in our case, we send somebody out on the 5th, the 12th, the 19th, and the 26th. And this graphical model on the bottom represents how many animals were actually there at each one of those survey times. So this naturally discretizes the actual process. So now instead of having a continuous process, we have this discrete process that varies between the different observation times. But we don't really know what exactly is happening between each one of these observations. To make matters worse, our observers aren't perfect. So when they go out to sample the population, they might miss some animals, they might count some animals twice. So in effect, what we end up getting is a noisy sample from the true abundance, which is generally an undersample. So we generally assume that the stronger effect is that we'll miss some of the animals. But that will give us data like this on the bottom, where we have in white, we have the true abundance at each time, and in gray, we have the actual data that we collect. So in the end, our data is just a vector of counts and the associated timestamps when they were collected. So this discrete version of the model, we classify as something called a latent branching process. So this latent branching process is essentially a hidden Markov model, where the main latent variable of interest at each time step are nk, which are the abundance, and the observed variables in a very, very light gray here are yk, okay? And these are governed by some observation or emission process. And we're gonna introduce two intermediate variables to govern the different dynamics that we're interested in modeling. So the first intermediate variable we call mk, and this is the number of individuals that immigrate into the population between these two time steps. And then we also introduce zk, which represents not only the number of animals that survive, but the number of new offspring that are produced by the animals that were present at the previous time step. And we're gonna lump these together into one variable. We'll see why a little bit later. But these variables control the entire model. And what's important about them is that each one of these latent variables in this model are unbounded integers. So they have support from 0 to infinity, right, on the natural numbers from 0 to infinity. And this is what makes them particularly difficult to work with. It turns out that unbounded discrete distributions are really hard to work with. Just as an example, suppose that you know the joint distribution of two of these latent variables. So somehow you know the joint distribution of nk minus 1 and nk, and you want just the marginal distribution of one of them. So you want just the marginal distribution of nk. Well, that's easy. It's a discrete distribution, and I know how to deal with I know how to marginalize discrete distributions. I just take the joint distribution and I sum over all possible values of nk minus 1, right? That's well formed. That's the correct way to do it. However, nk minus 1 has infinitely many possible values. So this sum is an infinite sum, and in general, there's no way to do this. There's no way to do this for an arbitrary joint distribution. For some particular distributions, you might get lucky and this will have a closed form, but in general, this is not possible to answer simply, okay? Furthermore, I said you just know the joint distribution, but what does that really mean? In a lot of discrete distributions, when we're talking about hidden Markov model, we'll often have distributions represented explicitly, where it's an arbitrary distribution, it's an arbitrary discrete distribution, I will just explicitly enumerate all the terms of the PMF. But in our case, this joint distribution would be a two-dimensional matrix with infinitely many rows and infinitely many columns. And you'd have to somehow explicitly enumerate all of those possible values, right? So there's no clear way to represent these either. And this isn't just a specific detail of how we set this model up. This is true of unbounded discrete distributions in general. There's really no good tools for manipulating models that include these kinds of latent variables. There's a couple of approximate techniques. The main one that's used in ecology, and the main one that I'll focus on in this talk, is to truncate the distribution. So essentially, if I have an unbounded support, if I have a latent variable that's discrete with unbounded support, right, in the top, this vector, I'm simply going to choose some value n to be the upper bound, and I'm going to say that actually this distribution just has support from 0 to n. Now it's a finite distribution, and I know how to deal with finite discrete distributions. This is commonly used in practice, so there's several models that use this. If you get the package that everybody in ecology uses to fit models like this, this is exactly the technique that they've been using for many, many years. But in practice, they're somewhat unsatisfying. For one thing, there's this question of how do you choose the value of this parameter n? So you could just guess. You could just set it very, very high and hope that you've captured almost all of the distribution. It's still finite, even if it's very high. Or you could try to do some kind of tuning mechanism where you keep increasing n, maybe you iteratively double it or something until you get convergence in whatever quantity, whatever statistic it is that you're trying to measure. But regardless, there's some amount of tuning that has to go into selecting this parameter. And regardless of how you do this, even if you just have a good guess, a conservative estimate for what n should be, the runtime of these approximate algorithms is fairly slow. Anecdotally, running a model, fitting a model using a conservative estimate of n can often take a little over a day for kind of small-ish real problems. For moderate problems, it can take like a week. And what this means in practice is that ecologists really aren't willing to try more than one different model. If it's going to take a week to fit a model, you're only going to try one. At least ecologists will. They're going to try one. Whatever comes out of the algorithm, they're going to take as gospel and use without trying a whole lot of different tuning, without saying, oh, well, what if I set it higher? Would it still have worked?
Can you hear me?
I can, yep.
So I have a question. So it takes a week. What kind of hardware do they run that on? Like it takes a week for like a desktop computer or like?
Yeah, so it's highly vectorized, so it's fairly efficient, but it is running usually locally. Ecologists typically aren't running things on like big parallel systems or clusters. There might be some room for improvement, but it's a pretty linear operation, so I'm not sure how much you could do with parallelization, but there are potentially some engineering improvements, but asymptotically, it's still pretty slow.
Okay, got it. Thanks.
Yeah.
Why is it slow?
There's a convolution is sort of the main bottleneck. There's a convolution that has to happen between the different dynamics. So how many of the new animals that you observe between time, t and t+1, those could be from several different distributions. So they could have been new animals that were reproduced. They could have been animals survived from the previous time step. They could have been immigrants, or they could have been any possible combination of all those dynamics.
So it's not really because of n, though?
It depends on n. So asymptotically, it scales with the value that you choose for n. I think it's n squared log n asymptotically with the value that you choose for that parameter. Okay. Okay. To me, the larger problem with these approximate solutions is that they're not really particularly well formulated, or I shouldn't say that. That's too harsh. They don't make any formal guarantees about the degree of approximation between the true distribution that's unbounded and the truncated distribution that you're using. Which means that we sort of don't have a very principled way for judging how much potential bias there is. And in fact, we've seen in our experiments that it's pretty easy to have a very realistic setting where you can sort of trick these truncated methods into choosing a very unrealistic value of n, and then that leads to biased parameter estimates when you actually learn the model. I think it's worth noting that like this has been used for a very long time. People are not necessarily frustrated with this model. I think they would probably continue using it, except that now we have a better way to do it. So our better approach, I call PGF Inference or PGF Learning. This is something that we've been developing for quite a while now. And at this point, I sort of think of it as like a toolbox for performing inference and learning in models that have distributions like this, where you have countably infinite support for discrete latent variables. And the technique has two major elements to it. The first is a solution to the representation problem I mentioned earlier, where instead of having these distributions that have infinitely many terms, and aren't really representable in the traditional way for discrete distributions. Instead, we use generating functions, which I'll describe in a little bit. And then once we switch to using generating functions as sort of our core operational unit, inference and learning reduce to function evaluation, which is sort of a different regime than we're used to, but can be solved very efficiently using Autodiff, which again, I'll come back to. This is sort of just the outline. The nice thing about our technique is that it is not an approximation. It is the exact method. So it is, you've designed a model that includes countably infinite discrete distributions, and we can solve it exactly. So we can actually compute the correct likelihood, the correct marginals. We can compute pretty much any statistic that you're interested in. We can do moments exactly with no approximation, subject to like numerical rounding. And in spite of that, despite giving you the exact answer reliably, it's also quite a bit faster than the approximate solution, somewhere between around 2 orders of magnitude faster than using this truncated approach, which we'll show empirically in results later. And at this point, one of the I guess the sort of new pieces of news, if you've seen some of this material before, I've been working on this for a while and I see a lot of familiar faces. One of the big new pieces of news for this work is we've got a really polished code base now that's pretty black box. So the code is available in Python, R, and C, and we're planning a code release, but the main missing task is mostly documentation. So the code's pretty nicely polished and commented, and if any of you are interested in poking around with it or seeing if it can help you solve any of your problems, please feel free to contact me after the talk, and I'd be happy to share the pre-release version of all this code with you. Okay, so let's dig into this PGF inference, PGF learning technique. So the main thing that we're going to focus on for today is going to be how to use these techniques to compute the likelihood in latent branching processes, the model that I just presented. This is going to have 2 major elements that I described. The first is going to be writing our favorite inference algorithm in terms of probability generating functions. And the second will be evaluating those functions using Autodiff. If we were, instead of interested in just doing inference, if we were interested in performing learning, that there's 2 different methods you could use. The first is sort of the naive approach. We have a function that evaluates the likelihood, so we can optimize that using gradient descent and just use numerical estimation of the gradients. That works pretty well. We have lots of results doing that. Or we also have a new paper that is going to come out at ICML this year, which uses a lot of the same Autodiff techniques to not only evaluate the functions, evaluate the likelihood, but also evaluate the gradients of the likelihood with respect to the parameters. I'm not going to get a chance to speak too much about that, but if you're interested, be happy to talk with you after about that paper. All right, so let's dig into the first part of this algorithm. So the model that we set up is essentially a hidden Markov model. So for a discrete hidden Markov model, the classical inference algorithm is called the forward algorithm. So the forward algorithm is a recursive method for computing the likelihood in a hidden Markov model. And it proceeds by recursively computing what are called messages. So the message is just a joint distribution over one latent variable and some subset of the observed variables. So in the forward algorithm, we define kind of the main message of interest is the alpha message. So this is defined as this distribution of nk and all the preceding yks. I don't think my diagram and my text will quite line up. But, so in the forward algorithm, the main meat of the algorithm that we're going to focus on is how to actually do the recurrence. So what we're interested in doing is, given this alpha message, so this joint distribution, I want to compute the next alpha message in the series. So I want the alpha message for nk and yk down to y0. Okay. So the way that this works, given this message, I multiply by the conditional distribution, which gives me this joint over 2 of my latent variables and 2 of my observed variables. I marginalize out this latent variable, and I'm left with this kind of intermediate quantity. So it's the joint distribution of this latent variable and these observed variables. We define this message as the gamma message, which just helps with some of the notation later in the talk. We're not going to spend too much time focusing on it. But once we have the gamma message, the next step is to introduce the last piece of evidence here, the last yk. So to do that, we just multiply by this observation distribution, and we're left with what we set out to get, the next alpha message. Okay. So it's worth noting that each of the messages, so each of the alpha messages and the gamma messages, are still probability distributions over one of the latent variables that have countably infinite support. So each of the messages also have countably infinite support. Okay, are there any questions so far? Okay. The next step is going to be, how do we adapt the forward algorithm to use what are called probability generating functions? So probability generating function is a relatively uncommonly used concept from statistics. It's an alternative representation for a distribution. So there's a one-to-one correspondence between the PMF of a distribution, the CDF, and the PGF. So every distribution will have a corresponding PGF. And the PGF is just defined this way. So a PGF F is a function. We usually subscript it by a random variable X, which describes essentially which random variable this which just describes the distribution that we're capturing in this generating function. And the generating function itself is a power series in some indeterminate variable S. So we see it's a power series where these are the coefficients, S is the polynomial terms, and these are the powers of the, or the degrees of the polynomial. Okay, and the coefficients of the power series are just the terms of the probability mass function. Okay. Now this wouldn't get us very far. This is obviously still an infinite sum, but what's nice about the generating functions is that for most distributions, pretty much any named distribution, the PGF has a nice closed form. So this infinite sum will have a closed form solution that's usually pretty concise and easy to write symbolically. So here's just two examples for some common distributions. The other nice thing about PGFs is that there's a lot of different ways to manipulate them symbolically. So in our first paper at NIPS, where we kind of introduced this idea originally, we collected a set of different manipulations, of different operations that you can perform on the generating functions of random variables. So just as an example, if you have two random variables, X and Y, and you know their generating functions, then the generating function of their sum is pretty easy to compute. You just take the product of those two generating functions for X and Y. Okay. Yes, so similarly, we can do marginalization. So this is a joint PGF, which I won't speak too much about, but marginalization is very easy. So I'd rather show this as an example with a univariate PGF. So if I have a PGF for some variable X, and I set S to 1, then you see instead of having an S here, I just have a 1. So all of these terms are going to be 1, and I'm left with just the sum over all the possible values of X of this distribution. Right? For a proper PGF, this will just equal 1. But in general, we're going to be working with unnormalized PGFs, which is not a detail that will come up again. So the next step then is how do I take the forward algorithm that we defined earlier and update it so that it operates on generating functions. So step one is going to be to define a set of generating functions to correspond to each of the messages in the forward algorithm. So this is pretty straightforward. I'm just going to, if I have the alpha k message defined this way is our definition from before, and I'm just going to define a generating function for this distribution. So I'm going to take the alpha k distribution, I'm going to set it as the coefficients of a power series in S, and I'm just going to call that the generating function for alpha. Okay. This is wrong. This should be nk. Okay. Similarly, I can do the same for the gamma k. So I can set up a PGF for the gamma k messages, which we'll just call big gamma. Okay. And then the kind of hard part is how do I actually define the recurrence so that given the generating function for alpha k minus 1, so given the generating function for this message, how do I get the generating function for the next message, the next alpha message? Okay. I'm not going to go through the whole derivation. We're going to just sort of show you what it looks like. If you're interested, it's not too bad. It's another thing that I'd be happy to kind of walk through with somebody in more detail after the talk. But for now, let's just look at what this recurrence looks like. So starting with alpha k minus 1, the PGF for alpha k minus 1, I can get the PGF for the gamma k message by taking my alpha k minus 1 message, and plugging in this PGF, evaluating it at this PGF. So this is the PGF for my offspring distribution, which combines both survival and reproduction, and the multiplying by the PGF for immigration. So this is the PGF for the number of new immigrants between these two time steps. Okay. Then I can complete the recurrence with this hairy piece of math, which we'll spend a little bit more time on later. What's important to note, so rho k here is just a constant. So this is all pretty much just a constant. Yk is my observed variable, rho k is a constant, and s is this indeterminate. So this is just a very low degree polynomial. This is the really hairy part of the recurrence. So here I need to take my gamma k message, evaluate it at s times 1 minus rho k. Again, that's just a constant. And then I need to take the ykth derivative of this PGF with respect to its input u. So this is definitely the hairy part, and we're going to spend a little while talking about how to do this. And it's going to be the main motivator for why we need to bring in Autodiff. Okay. So here collected, so this is the complete recurrence that we just built up over the last couple slides. That relates alpha k and gamma k, the PGFs for alpha k and gamma k. Okay. And what's nice about this is that once we're done, once I have alpha sub capital K, so I have the PGF for the last alpha message, if I evaluate it at 1, I just am left with the likelihood. So we can sort of see why this is if we have, so if this is the end of the chain, so this is n sub capital K, the last latent variable, and I have this message, if I evaluate it at 1, I marginalize out this latent variable, and I'm left with just the joint distribution of all of my data. Okay. So, so this is about as far as we got with our first paper on this topic. To summarize kind of what we did, so our first idea was to kind of approach this symbolically. So this is just the symbolic recurrence and doesn't give you any real idea for how to actually go about implementing it. What we found at first, the most commonly used model in ecology has immigration that's Poisson, survival that is binomial, and no reproduction. That's a very common model. And so it turns out that with that model, you can just evaluate these symbolically, and all of the messages will have a symbolic form that stays in a particular closed form that is very concise. We got really, really excited, and you can read our paper and see how proud of ourselves we were for discovering this. And we thought we kind of solved it. And it turns out that we really just got very, very lucky. As soon as we tried any other model, we found that this doesn't hold up. The recurrence is correct. I mean, the recurrence is correct. But if you just try to evaluate this symbolically for any model in general, except for the one that we got lucky with, the symbolic representation explodes. So if you just imagine sort of unrolling this recurrence, you have these high order derivatives. I mean, yk is fairly high order. These are the magnitude of our observed variables. So as we keep unrolling this recurrence, it kind of explodes exponentially. And was just grossly intractable, even with some really fancy symbolic math libraries. This was just really not a good way to go about it. Yep.
What are the derivatives taken with respect to? Is it the u variable?
Yeah, it's with u. So here I'm kind of, I'm occluding u. So s times 1 minus rho k is u.
Gotcha, thanks.
Yeah, so if you look back and like plugged, so here's gamma k, if you were to plug this into this step of the recurrence, you're setting u equal to s times 1 minus rho k. Good?
Thanks, yeah.
Okay. Any other questions? Okay. So that wasn't too successful. But our big insight was that if you try to do this symbolically, what you're trying to do is you're trying to compute the symbolic form of each of these PGFs exactly. But there's not really any need. At the end of the chain, when we get to the end and we want the likelihood, we don't need to know the symbolic form of alpha k. We only need to know what its value is at 1. And this is true, actually, if you kind of step back through the recurrence. Each of these generating functions, we only need to know their value at 1 point. So we're going to need to know alpha k at 1. We'll need to know gamma k. You need to know the yk derivative of gamma k at 1 times 1 minus rho k. We'll need to know this at f of 1 times 1 minus rho k. But in the end, we're only evaluating each of these PGFs at a single value. And maybe their derivatives at a single value. And this is pretty much exactly what forward mode Autodiff is set up to do. So this was the next branch that we went down in this, and turned out to be super successful. So let's dig into that. Before we do, we're going to focus for this section. We're going to focus on this piece of the recurrence, the hairy part that I described earlier. So since this is kind of hard to parse, it's just a lot of math. We're going to break it down here in this computation graph. So this is just, for those of you who haven't seen one of these before, this is just kind of a nice way of graphically representing what is happening in a complex equation. So we see that the edges in this graph in this computation graph correspond to like intermediate quantities, which in this case are all scalars, and the nodes correspond to components of this computation. So when the elements of the computation are all primitives, pretty much any one of the mathematical primitives, we'll just kind of group them all together into a single node. This is recursive, so we're kind of hiding what's actually happening inside this gamma k block and the alpha k minus 1. This is kind of recursively going deeper and deeper and deeper until we get to the base case, which I've left out. But okay, so once gamma k is finished running, it's going to return some scalar value, which we'll call little gamma here, not to be confused with the message. This is an unfortunate piece of terminology overloading. So this is also just a scalar value. And now I get to this node in the computation, which is, okay, you've got a scalar value gamma k. Now take its derivative yk times with respect to u, the input to this function. And that's a real puzzler. That's really not obvious. So if we were just doing this naively, this is where our computation graph is going to get a little tricky. But this is where Autodiff is going to step in. So the key idea behind forward mode Autodiff is, let's just say I have here's just one possible node in my computation graph. So this is just a primitive. So this is just a node that takes in 2 scalar inputs u and v, computes their product, and returns it as y. Okay. Now, if this is great if I just need to know what the value of y is, but if I also want to know the values of y and the derivatives of y with respect to some fourth variable, in this case it's going to be x, then I can use Autodiff. So in Autodiff, we're going to replace these scalar inputs with dual numbers. So a dual number you can think of as just a data structure. So it could just be a list that contains the scalar value, in this case u, and the scalar value, which is the value of the derivative of u with respect to x, and then possibly some number of higher order terms. So this is higher ordered Autodiff. There could be as many derivatives in these dual numbers as you want. And if we replace both of the inputs to this computation node with dual numbers, then now I can do what's called lifting. So now this computation node is expecting two scalars, but I'm going to replace it with the lifted function. So the lifted function is a function that takes as input 2 dual numbers and returns the corresponding dual number for their output. So if I give it u and derivatives of u with respect to x, and v and derivatives of v with respect to x, it's going to give me back my output, my original scalar output y, but also the derivatives of that variable with respect to x. Okay, and this is called lifting. For most primitive operations, this is pretty well known. They're not too hard, actually. They're pretty cool. And the actual implementation typically uses something called truncated Taylor polynomials, which is essentially just a polynomial. So we are actually going to store the dual numbers as a list, but the list is going to have the coefficients of these polynomials. And then in practice, this is typically done in like a black box way. So using operator overloading and function overloading. So in most Autodiff libraries, you as the user don't really know that this lifting is happening. If you write a function that uses u times v, and then you replace u and v with dual numbers, then the Autodiff library that you've imported will just overload the times operator and call the lifted version instead of the scalar version. So it's usually pretty invisible to the user, which is a really nice design style. Autodiff is really cool. Okay, so how do we actually use this for our problem? So our main goal is going to be to lift everything in this computation graph. So at the top level, we're going to try to lift alpha k, this big function that contains basically everything in this picture. Sorry, I'm a little sick. Okay, so to start off, we're going to replace the inputs to alpha k with dual numbers. In this case, we'll see why later, but in this case, we're just going to use dual numbers for its inputs s and with the derivatives taken with respect to themselves. This is really easy to do. S ds is just 1. So these dual numbers are very easy to construct, but we're going to start there. And we're going to start propagating these through the computation graph. These two next nodes are both comprised of just primitive operations, so lifting them is pretty trivial. And then we're going to continue propagating these dual numbers through the graph. Here, now I have a dual number with the value u and the derivatives of u with respect to s. When I lift gamma k, it's now going to return a dual number for the original scalar value and the derivatives with respect to s. But now I run into a problem. I did all of this work so that I would have the derivatives of gamma and their derivative. I'm sorry, that I have the value of gamma and their derivatives with respect to u. But I've just done a whole lot of work to compute the derivatives of gamma with respect to s, which isn't really doing me a whole lot of good. So instead, we're going to rewind. Let's go back to this step. And here I've got a dual number where the derivatives are with respect to s. I want a dual number where the derivatives are with respect to u. At this point, it's actually very easy to do this. I'm not going to, these dual numbers are very simple. So this is the dual number for u du. So again, it's just like this original input where all the derivatives are just 1. Or sorry, the first derivative is 1, all the higher derivatives are 0. So this is very easy to compute. So I'm just going to break this here. And now when I lift gamma k, it's going to give me back a dual number with respect to u. So it's going to give me a dual number for gamma and the derivatives of gamma with respect to u. Now that this computation graph is really easy, I've actually got exactly what I need. So I can just continue on, and I run into my second problem. Here, this is also just a simple node. This is just taking the product of this value and this value. But when I try to lift it, I've got the inputs are 2 dual numbers, one that has derivatives with respect to s and one that has derivatives with respect to u. So this is the major part where standard forward mode Autodiff actually can't get us any further. So in our ICML paper last year, we tackled this particular problem. And we showed that you can introduce a new operation called the compose operation. So this operation allows you to take 2 dual numbers that are defined. So you have some variable VL and derivatives with respect to VJ, and another dual number VJ and the derivatives with respect to VI. And you can compose these into a dual number for the original variable VL and its derivatives with respect to VI. So if we look at what this actually looks like in this example, we have dual numbers here. So these are derivatives of gamma with respect to u. We have here, these are u and the derivatives of u with respect to s. If we compose these 2 polynomials, then we get out a dual number with gamma k and the derivatives of gamma k with respect to s. So now we're back to having a dual number with derivatives with respect to s. When we pass this into this node here, we can lift it just fine. We can lift it just fine. No, okay. We can lift it just fine and finish the lift. I'm missing one step here. Okay. The key takeaway is this is kind of a small extension to forward mode Autodiff, but with it you can use Autodiff on computation models that have nested higher order derivatives. We show up here because of the PGFs, but this is true in just about any model where you see these nested high order derivatives. You can use this operation. Okay. For this algorithm, so for the lifted version of the forward algorithm, the asymptotic runtime is given here. So it's k y squared log y. So k is the number of observations, which is also the number of recursive layers that we have in the model. And this y squared log y is the runtime of the compose operation. So for us, the major computational bottleneck in terms of lifting this function is that new compose operation. It requires you to do the composition of two polynomials of length y, where in this case the y is the sum of the magnitudes of our observed variables. Okay. So this is the main runtime bottleneck. But this is not really, we think, too bad of a runtime, and this is certainly still polynomial. And having an inference algorithm with runtime like n squared log n is not too bad. In our case, k is going to be a small constant, so y is kind of the main problem size, parameter, and you know, n squared log n we don't think is too bad. But regardless, this is the first algorithm that achieves polynomial time inference for this family of models. So to compare this, there's not a whole lot of other methods to compare against. So we have two that we're going to compare against empirically in simulated problems. The first is the truncated method that I described at the beginning, the approximate method where you sort of set an upper bound. In this case, we performed tuning, so we found the lowest value of the truncation parameter, such that the likelihood was within epsilon of the correct value. Then we just reported the runtime. We sort of assumed that you had an oracle who told you exactly what that value was, and we just reported the runtime of the algorithm on the lowest possible value of n that it could use and still get an unbiased answer. The second baseline method here is called PGFFA, which was this really, really fast method that we had that only worked for one type of model. So it's very, very fast, but only if you're doing this one particular type of model. Okay, and we see that in our studies, the exact method that we just presented is quite a bit faster than the approximate truncated method. Even when the truncated method, we're sort of not charging it for any of the tuning that it had to do, and we're using the lowest possible unbiased value, we're still faster by quite a bit. Okay. Yep. Since this first paper, we've also been doing a lot of engineering to try to improve the method. So most recently, we've adopted a new number system, which is kind of an interesting engineering detail. It turns out in these truncated Taylor polynomials that we use for Autodiff, you have very long, you require a lot of derivatives. You have a very, very long dual number with a lot of terms in it. And the relative magnitude of the smallest and largest is extreme. You have extremely small values and extremely large values. So typical like log space tricks don't quite work. So instead we had to adopt like a whole new number system that I won't go too into, but the punchline is that it scales more or less infinitely now. And even with the stability improvements, it's still significantly faster than the truncated method. So this is runtime. It's actually a slightly more favorable experiment for us. But we see that compared against the truncated method, we're 2.5 times faster than the naive truncated method. This in yellow, this is the truncated method using a fast Fourier transform, which is a nice speed improvement for truncated method. But if you actually look at what's happening when you get to low probability regimes, so when you have parameters that are very unrealistic, the truncated method with the FFT actually starts to break down. We're not totally sure why, but it pretty reliably starts to break down in low probability regimes due to some instability in the FFT, probably. So even though it's a little bit more favorable to compare against this one, I think the fairer comparison is against this kind of more reliable direct convolution approach. Okay, how am I on time? Pretty much over. So I'm not going to talk too much about learning. Like I said, learning in this model we've been doing for a long time, where we just use sort of naive approach. We just take gradient descent and compute numerical gradients. If you're interested, we do have a new paper that I mentioned where you can compute. You can use some of the same tricks to evaluate the likelihood. You can also evaluate the derivatives, the gradients of the likelihood with respect to the parameters, using a little bit more complicated autodiff. It's called forward over reverse mode autodiff, and that paper will be coming out soon. I can share the preprint of that with anybody who's interested as well. So with that, I'm going to wrap up and take questions if anybody has any. Thank you.
So if no one else has a question, I'm going to ask, how did you get started down this route of looking into PGF representations? Was it mostly because of the infinite sums and the infinite number of terms, or was there something else that led you to trying to manipulate them?
Yeah, it started off as a alternative representation. So we were feeling kind of stumped. We had tackling this problem, we had an approach using a Gibbs sampler, and that worked pretty well. But it was kind of unpredictable and not a whole lot better than other approximate methods. And we thought that the key problem was this representation. So Dan is the one who stumbled on the PGF. I mean, I haven't really seen them used too many other places. You see moment generating functions a lot, but the PGF is, I think, lesser known, certainly, than the moment generating function. But yeah, once we stumbled upon it, there was this kind of idea, well, we could use this as a representation, and we could redefine everything. If you just replace the probability mass function, you could pretty much just replace it with the PGF, but how do you actually manipulate them? And that was the bulk. We spent a pretty long time deriving all of the different operations for PGFs back when we wrote the first paper. But yeah, does that answer your question?
Yeah, thanks. That's really cool. Yeah, because I haven't seen PGFs used just widely. Like you said, it's mostly moment generating functions. But I was wondering, that was really cool that you found out about it and then were able to adapt it to solve your problems.
Yeah, we're actually looking right now. So one of my open questions. So there's a couple of ways to convert between a PGF and an MGF. And we are, I'm currently looking at ways to do approximate PGF inference. So the idea would be that could you construct a moment matching? So if I have a PGF for a distribution and I've manipulated it using all the tools that we've developed already, but I have many terms required for that, could I project it to a simpler model that has the same moments up to a certain point? Yeah, I mean, I'd be happy to talk a little bit more about that at some point, but it would be more than the 10 minutes we have scheduled. Yeah. Any other questions? All right. Well, I guess thank you everybody for coming. I believe we have another speaker lined up in 2 weeks. Is it Neil? I forget who is on docket, but we should be having another talk in 2 weeks from today. So hopefully see you all there.
Thanks for a really great talk.
Thanks.